Who would have thought? Yeah, right, that's right, Greg. All right.
All right, sorry for the technical difficulties. It's my pleasure to introduce Danielle Eckert and Craig Roberts. They're here to talk to you about Regrinder Run and Reclaim project with, it's done with SRG Global. I believe Danielle works there.
Thank you, Dr. Davis. Good afternoon. My name is Danielle Eckert. This is Craig Roberts. We're working with SRG Global and the Regrinder Run and Reclaim project. And this is our senior design presentation. For our presentation, we'll be going over background about who SRG Global is, what is injection molding, our objective statement for our project, as well as our project design and our budget. So to get started, who is SRG Global Incorporated? They started out as a glass company in 1932 as Guardian Glass, where they manufactured windshields for vehicles in the automotive industry. In 1968, they became public as Guardian Industries Corporation. In 1982, they bought a company called Windsor Plastics. This company dealt with injection molding in the automotive industry. Then in 2008, they bought the company Siegel Robert Automotive. At the time, this company was the largest manufacturer of coatings on plastic in North America. With the purchasing of these last two companies, they created a subsidiary of Guardian Industries called SRG Global Incorporated. This company has many different facilities around the world, one right here in Evansville. Their main revenue comes from creating plastic grills for customers like Honda, Toyota, Ford. Here's an actual enlarged picture of what the grill looks like on a Toyota Tundra truck. This assembled grill is actually made up of multiple plastic parts that have been assembled together, one of which is actually our project focus, and we'll get into which part that actually is. But for now, with these parts that we create for our customers, they all start in the injection molding department. The one here in Evansville has 26 injection molding machines. These machines are used to create those plastic grills for our customers. There's 400 different molds. A mold is just the negative image of what the part looks like. So we can use it to create the part. And then 39 different plastic resins. The resin is just a material that's melted and injected into a mold to create that plastic part. So with all these different options and the fact that we're dealing with a recycling project of reusing plastic material and sending it back through injection molding process, we thought it'd be best to start in the injection molding process.
So there are many components to an injection molding process here, and one of these components is the injection molding machine itself. We also have the barrel, which takes the resin that's in a hardened form, turns it into a liquid form, and injects it into the mold. We've got a video for you, so I'm going to walk you through it. So first, the resin is hardened and in pellet form, and it's fed through the hopper into the barrel. Then the screw will move forward, pushing the resin, and it will be melted by the time it reaches the nozzle here. The resin will be injected into the drop zone here, this center spot, and then it will spread out through the excess material here called runners. These runners then, or the resin will then fall into the cavities here. Each cavity represents two different parts. The excess material here is what we are actually focused on. And everything produced is a shot. But we are focused on this excess material. We're going to take it, chop it up, send it back into the injection molding process. So to summarize a little bit of what I just said, the resin enters the hopper, it is then melted, injected into the shot, and a shot is created. The objective of our project is to design a regrinding process that will not interfere with current daily production, not degrade the quality of the product, to standardize the regrinding process for future implementations, and have a 2-year payback for the system. The focus of our project was the Toyota Tundra air intake, and as Daniel pointed out before, this is the truck that it's actually put on. Our part is located directly behind this section of that plated grill, and since it's behind it, you don't normally see it during normal use. Down here, you see a full shot of our part. That's what comes out of the mold initially. What we are planning to focus on is this excess material connecting these two separate parts. These, again, are called runners. These are what will be reground and sent back into the process. What I want to walk you through now is the actual injection molding process spent or done at SRG Global in Evansville. This is the side view of an injection molding machine. This injection molding machine is much bigger than the one you just saw in the example. But what you see here is the mold. This is one half of it. The other half is right here. And it's opened up already. The shot has been created. It's been cooled. It's about to be taken out. The shot is right here. We're about to see a robot arm swing in, once I start the video, and take it above the injection molding machine. So there's the robot arm. It grabs onto that shot and lifts it out of the molding machine and above. And then we see it here. You'll see it swing over to something called a degator, which is right here. This degator consists of 8 different knives lined up perfectly to cut that excess material off. That excess material will then fall through a chute into a scrap bin. And since that excess material is gone, that shot became 2 parts. Those 2 parts will then swing back over to this side of the machine and be placed into these bins that you see here. The bins will go down the conveyor belt and then be shipped off to Toyota.
So for our project, it was broken down to 3 subcategories. The first being the actual regrinder process. Since we're reusing plastic, we want to know the steps that it will be going through after that injection molding process. The next subcategory is the layout design. We have an old layout, and we're trying to move to the new layout, and we'll discuss some new implementations to make that happen. Our last subcategory is the design of experiment. This is to test for quality to make sure that the resin doesn't degrade far enough to where it will create a defective part. For the actual regrinder process, normally, like Craig said, the runners drop through a chute into a scrap bin where it's collected. Instead, we want the runners to drop through that chute into the top of the grinder here, where the runners will then travel down that wide chute into 3 rotating knives, where the runners will then be chopped up into small particles, also known as reground material. The reground material will then be sent through back to the hopper. You notice here there is 2 main hoses that are connected to this hopper. One is for the reground resin hose, and one is for the virgin resin hose. This is because we can't just make a part from reground material. We have to mix it with some virgin resin so we don't create a defective part. So with implementing a process like this, we have to, there's some concerns involved. One being blending equipment. It can be very complex and expensive. So for our plant, we had something in-house already that will not only allow us to mix the material, but allow us to pull different ratios between the reground and that virgin resin. It's called a dual ratio valve, and I'll show a picture in just a minute what that looks like. Next is batch control. An example of that would be the customers want to know how much reground material is being put into the part. We can tell them how much we're setting the dual ratio valve to, but we can't say for accuracy wise how much reground material is going to eat into each part when it's being created. Another concern is chemical breakdown of the resin. The resin, when we first receive it to our facility, has additives inside of it. So once we start regrinding the material and sending it through a heating cooling process again over and over called thermal history, the resin can start to break down because the additives start to disappear from it. The last concern is that the resin starts to become darker. This is one reason why we picked our part, because that resin that is used is black resin, and so the resin cannot become, it's not noticeable. Moving on to our second subcategory, which is the layout design. Going from the old to the potential new layout, we had to implement a couple items. The dual ratio valve highlighted with this square right here. Again, you see those 2 hoses that allow that reground and virgin to enter the hopper. Our next implementation is the replumbing of the water lines. This is a very busy picture, so I'm going to enlarge it for you. And focus right here towards the bottom where the water lines are located. They're actually on the ground. This is a very limited space to begin with. So replumbing these to a different location will help us with space, since we want to implement the grinder right next to the scrap bin located there. If we were to replumb these water lines, we have to be aware of the thermolators that sit in front of the molding machine. These thermolators are used to cool down the mold to solidify that part that's being produced. One other concern with having the water lines on the ground is the hot runner panels that are straddling the water lines. The last concern we had was the actual scrap bin that's sitting on top of the water lines. Since we want to implement a grinder right next to the scrap bin, it's hard to put a grinder right next to it on top of it. One, because it's really heavy, and two, it's not really one to sit on top of them. So we went ahead and replumbed them. The bottom left shows the water lines where they used to be, and the top right is where they're no longer existent. Another implementation we had to do was redesign the chute. Our part is not the only part that runs on this machine. There's other parts that also run on it. So the original chute is a one-tunnel chute where the runners are clipped from the gator that sits on top of the chute, located here. The runners will then fall down into a scrap bin located beneath. Since we want to put that grinder right next to the scrap bin, we went with the initial design concept of having a two-tunnel chute with a door hinge in between, where any other part that would run in the molding machine would be flipped to the right, allowing all excess material to flow into the scrap bin. And then when our air intake would run, the door would be flipped to the left, allowing all runners to fall into the grinder. With that initial design concept, we were able to put some final dimensions. One, which is the isometric view here. That's just to give you an idea that it still has that initial design concept of one tunnel going to the scrap bin and the other going to the grinder itself. But another implementation, since we're adding another machine to the area, we have to extend this maintenance platform that's located right behind this original chute to make way for that grinder that I talked about. You can also see how the hot runner panel is also missing. This is because once we extended the platform, there's no more room for the hot runner panel to be there. And then that leads us to the next implementation, moving the hot runner panel and thermolators. And then the last implementation we had to do is the actual grinder itself.
So what you see here is an overview of press 26 and 27, or injection molding machine 26 and 27. The parts that I want you to focus on here are the blue and the yellow sections. The blue indicates parts that we aren't dealing with. We're not redesigning, we're not moving. And then the yellow shows the parts we are worried about. The conveyor you saw in the video earlier, the robot you also saw, and then here's the degator location. We also have a platform that we won't be able to move. This platform allows access for the mold setters to go in and change out the molds when other parts are being run. And then those stairs that allow access to that platform. One important thing here for the dimensions I want you to look at is the 6-foot space here. It makes it very limited, so we can't really put a whole lot of machinery there added to what's already in place. What we are messing with is the thermolators, the water lines, the hot runner panels, the maintenance platform and ladder, and then the chute and scrap. So the first step of creating the new layout was to remove those plumbing lines, as Danielle mentioned earlier. We relocated them underneath the injection molding machine, and as she said earlier, the thermolators are actually hooked to those plumbing lines. And so we had to move the thermolators in a way that they still had access to those. We ended up relocating them at the back of the machine here. There's a nice overhang where they can fit perfectly and stay out of walkways. We also want to move the hot runner panel to the front of the press here, and so that we can extend this maintenance platform. We will then implement the new chute instead of the old chute, move the scrap bin toward the front of the injection molding machine, and then put the regrinder or the grinder in place. So when putting any new process in, you need to test to see, does it work? Does it mess anything up? So I want to remind you guys of what the injection molding process really consists of. We start with resin entering the hopper. The resin is then melted, it's then injected into the mold, and the shot is created. After this, the part will continue. We saw this in the video. After the shot's created, the runners have to be clipped to create those two separate parts. Those runners normally will then fall into a scrap bin through that chute we talked about. What we want to put in is 2 steps after cutting here. The runners are clipped but then the runners will, instead of going into a scrap bank, go into a grinder. That grinder will then chop up that material, send it back into a dual valve ratio where we mixed and it with the virgin resin and then sent back into the injection molding process. So, the manufacturer also stated that one big thing we have to worry about is the degradation of that resin. Danielle mentioned a little bit earlier about how it discolors, but another thing that can happen is that after 6 generations, or heating and cooling cycles, they can also cause a defective part. We also knew that the manufacturer suggests a maximum of 30% reground material used as the shot weight. This means 30% of the total weight of the shot is made of that reground material. The other 70% will be virgin. We ended up choosing 20% instead of that 30 for quality assurance measures, and we also know that a sister plant uses the 20% to 80% ratio.
So for the DOE experiment, we're going to be testing for 3 criteria. First being brittleness, to make sure that the part doesn't break after it's been made at our plant and during its normal use. We'll also be testing for melt flow, which is just flow per minute or grams per minute. This is to test to make sure that it doesn't affect the injection molding process like we explained earlier. And then lastly, to make sure there's no spike in visual defects. The last 2 columns are actually blank because we have not yet completed the experiment because we're waiting on production timing to implement all those new items and to run this experiment. But this is just for your reference, so to explain that we're going to test them back to back. The reason for this to make sure that all variables are consistent as much as possible, and that the only thing that is really changing is the 100% resin versus the 80-20 reground resin use. Moving on to our budget, for just implementing the grinder alone, we would save 14 cents per shot made, meaning for every 2 parts we make, we can save 14 cents. In a year's time, we can save up to 10 grand a year. This was using last year's production data. Including that in our payback analysis along with plumbing savings. This plumbing savings was an average out of 3 other molding machines that were also replumbed. We had an average savings over 4 grand. Our total cost for the SRG budget was over 26 grand, making our payback period 1.8 years. So we met the 2-year mark that we explained in our objective statement.
So to reiterate that objective statement, our goal was to design a regrinding process that will not interfere with current daily production, not degrade the quality of the product, to standardize the regrinding process for future implementations, and have a 2-year payback for the system. We ended up choosing injection molding machine 27 to implement this process. We know that the regrinder process will not interfere with current daily production due to the DOE that we're going to be performing shortly after school is out. We also, the process will also save money and have a payback period under 2 years. And SRG Evansville will gain a more organized process for implementing a grinder at other injection molding machines. We'd like to acknowledge SRG Global for allowing us to do this project. Specifically, we'd like to thank Micah Moore, Luke York, Jack Shepard, Paul Fletcher, Billy Freeman, and Donnie Stevens for helping us out throughout the process. We had plenty of questions, and they were always willing to help. And the entire injection molding team for allowing us to take up space in their office during different points throughout the semester. We'd also like to thank USI, specifically Dr. Davis, for being our advisor and helping us out throughout the process. We'd like to thank Dr. Smith, Dr. McDonald, and Dr. Kissel for sitting in on presentations and helping us practice. We'd like to thank Dr. Mitchell for everything he does in helping the department run well, and the entire engineering faculty for getting us to where we are today. And then the Pott College of Science, Engineering, and Education for all the opportunities given us throughout the year, and Mrs. Donna Moore, the administrative assistant, who is awesome and has helped us throughout our time here at USI.
All right, questions?
I'm just curious, did you have any consideration for any potential dusts coming from the regrind process?
Yes. We're going to put instructions in place to make sure that no leftover material or they'll pieces are left over in the grinder or in the actual chute itself. It's like a poke yoke, so it's stick proofing.
All right, I have a question on the, so the resin, you don't want to cycle it through more than 6 times, correct?
Yeah.
So how do you prevent that from happening? What's your strategy? Or do you shut down the line? What do you do to make sure that there aren't any particles chasing through the system more than 6 times?
We just talked about that earlier. Well,
The DOE experiment will help us with that, that test to make sure after so many times, after 100 times, that we don't see that defective part. That's kind of our checking system. We did do a theory calculation to make sure, but the concrete answer or the test would be from the DOE experiment.
Okay. Other questions? All right, let's give them a hand.